Hi, this morning we're going to be taking a look at indefinite integrals and talking about the indefinite integral, which is tightly related to the definite integral and also the antiderivative. Basically, we're going to get this symbol right here. Okay, that's the integration symbol, the integral. And we're taking the integral of little f of x dx. All right, and notice that this integral has no bounds. So it has no bounds on it. It doesn't tell us from where to where. So basically what we're asking is we're asking what is the integral of a function, and what we're going to be expecting is a function back. And it turns out that that function, and this should be somewhat expected, is big F of x, our antiderivative. Such that, right, big F of x prime is going to equal little f of x. So essentially what we're saying here is that f of x, the integral of f of x dx, little f of x, is going to give me the antiderivative. Now, this f of x is the general antiderivative. Okay, so it's going to have the plus c part. It's going to have that constant attached to it. And that is going to be one of the primary differences between that and the definite integral. The definite integral will give us a value. The indefinite integral is going to give us a function. Okay, so indefinite integrals give us, okay, and specifically the general antiderivative. This is pretty much the last kind of theoretical piece that we're going to need in order to understand what an integral really is. So we've already seen that an integral is basically the area underneath the curve that we can evaluate using the fundamental theorem of calculus. We know that the derivative of the integral is just the function that we have that we're evaluating the integral on, right, from the fundamental theorem of calculus. And we also know that essentially if we take a bounded or a definite integral, that we're just going to evaluate the antiderivative on a certain set of bounds. Okay, this is the last piece. This is basically saying, well, what if I don't have a set of bounds and I just want to be able to have a function, much like we had with the derivative, where we didn't want to know a specific value at a specific point, but instead we just wanted to know what the function was. Okay, so that's what this is. So let's evaluate an integral, and then what we're going to evaluate is we're going to evaluate 1 over x squared dx. Okay, and we're going to take this fact that this is going to end up equaling big F of x. So it's going to end up equaling the antiderivative of 1 over x squared. So that's going to essentially be, that's going to be x cubed over 3 plus c. That's it. So just like taking the antiderivative, we're going to take the antiderivative of this function here, okay? And that's x cubed over 3. And then we make sure that we add the plus c, because what we have here is the most general antiderivative. Notice that we haven't actually evaluated x cubed over 3 anywhere. Instead, we've just basically said, okay, now we have a new function. So let's evaluate this integral. The integral will be 1 over x squared dx. And just like when we were doing antiderivatives, I want to actually rewrite this as the integral of x to the negative 2 dx. And so, using the power rule, or that inverse power rule that we use for the antiderivative, what we end up with is we're going to end up with x to the negative 1 over negative 1 plus c. Okay, and so that equals 1 over x plus c. And that is the integral of 1 over x squared dx. Yep. The indefinite integral is the general form of the antiderivative. That's it. Let's evaluate another integral. And this time, we'll take the integral of cosine theta over sine squared theta d theta. And this is going to then be, what we're going to do is we're actually going to get this into a form that we can find the antiderivative. Okay, so we'll notice that this is going to be the integral of 1 over sine theta times cosine theta over sine theta, which equals the integral, and this is going to be then cosecant theta times cotangent theta d theta. And what we want to notice is that that is the derivative of negative cosecant theta. So the antiderivative of cosecant theta, cotangent theta, is cosecant theta plus c. And there we go. We can basically use this principle then to evaluate some other integrals. Definite integrals, definitely. Okay, and this is going to become one of those methods that you're going to use over and over and over again. Okay, so let's say, for example, I want to take 0 to 2 of x cubed minus 6x dx. And I'm going to actually do this two different ways. I'm going to first, what I'm going to do is I'm going to break up this integral, because I can break it out from 0 to 2, x cubed, and then this will be minus 0 to 2 of 6x, and then these are both dx. Okay, and that's one of those rules of integrals that we can do, right? We could break up subtraction, we can bring everything back together via subtraction or addition, right? And also scalar multiplication. So the antiderivative of x cubed is going to be x to the fourth over 4. Now, we don't need to actually use the general form. Instead, we can just evaluate that one from 0 to 2, because what we learned before from the fundamental theorem of calculus is that you can pick any antiderivative that you want. You don't have to actually choose the general antiderivative. You can just choose this one. Now, we subtract from that the antiderivative of 6x, and that's going to be 6x squared over 2, and we'll evaluate that one from 0 to 2. So this one, the first one, is going to be 2 to the fourth over 4 minus 0 to the fourth over 4 minus 6 times 2 squared over 2, or actually 3 times 2 squared, minus 6 times 0 squared over 2. And we'll evaluate those, and this gives me then, that's 16 over 4, so that's 4 minus 0 minus, and this will be 12 minus 0, so this ends up equaling negative 8. And so essentially what we've done is we basically, we've evaluated utilizing the antiderivative, we've evaluated the integral, found it on its bounds just like we did before, and then solve for those values. Now we can do this in an alternative way. In fact, we don't actually have to break these up. And as you get better and better at antiderivatives, you won't. So we take x cubed minus 6x dx. That's going to then equal the antiderivative of x cubed minus 6x is going to be x to the fourth over 4 minus 6x squared over 2, evaluated from 0 to 2. And we'll just simplify that now to x to the fourth over 4 minus 3x squared, evaluated from 0 to 2. So now we'll put that in. We'll start out with the 2's. So that'll be 2 to the fourth over 4 minus 3 times 2 squared minus, and this will just be 0 over 4 minus 3 times 0. And so this ends up equaling 4 minus 12, okay, minus 0, which is just going to equal negative 8. So either way that we do it, we're actually going to end up getting the same exact thing. Okay? So that's the big thing about the indefinite integral. Let's take a look at a quick review. So the things that we should remember is the indefinite integral gives us a function. And that function is the general form of the antiderivative. So it's going to be that f of x, or big F of x plus c. Okay? So remember, don't forget the plus c. Okay? So what you're going to do is you're going to evaluate what the antiderivative is, and then you'll have the plus c, where we can actually evaluate that integral if we were given, say, for example, an initial condition, versus, right, definite integrals give us values back. Give us numerical values. And sometimes we got to go find them, use a calculator, that sort of thing. But at the end of the day, they are going to give us some kind of numerical values. So this completes the lesson.